your warm-up and then hand me a warm-up?
That was like the biggest lie, because I'm going to underline my name. I enjoyed that. I'm not going to give it.
Do it.
I can't get it.
Thank you.
You know what? At some point, I stopped caring. And so, I was trying to get through class. I don't even care about passing.
There you go.
He's talking about, like, I'm passing. He's like, oh, no, this class. Like, all my other classes, I'm like, oh, let me get my
All right.
work in.
So the limit that's right there represents, in the shortest possible way, f prime of 2. You could have written a little more in terms of words, like the derivative of that function at a particular point. In this case, you know the particular point is 2. Now, if we had like an x here instead of a 2, it would just be the derivative of the function, period, at any old x. But because I have a number there, it's at 2. So on your final exam, you're going to have a couple of these sort of things on the multiple choice where you have to recognize, oh, that limit is just a derivative of some function. We might come out and tell you the function's this, or we might kind of embed the function within the limit thing, and you have to identify that. So we'll probably do that a little bit tomorrow for the warm-up. So we're going to recognize your limit definition of the derivative, and then be able to use the derivative rather than like the actual limit. So for evaluating the limit, you're not going to want to work through that limit process. You want to take the derivative and plug in 2. So your derivative, f prime of x, is going to be 6x plus 4 over x squared. So remember, that's 4 times x to the negative 1. So then you have multiply the negative 1 down to the negative 4 in front. So that gives you a plus 4 times x to the negative 2. And then you plug in 2 for your x, and you have 6 times 2 over 4 over 2 squared, and that's 13. So that limit turns out to be 13, but don't do the limit, do the derivative plug in 2. Any comments, follow-up questions for this? All right. Homework questions. What do we want to look at? On the whole, how do you feel like it went? Better or worse than 3.1? Oh, good. So, comments, questions, homework?
I have a question about the delta math.
Yes.
So one super long thing,
Yes.
like, do we have to do that or not?
Oh, yeah, so about that. I brought this up in block 3 yesterday. Would you like extra credit?
Yes.
Okay, do that. So, the one super long delta math, that's like for final exam review. The more you do of it, the more extra credit you can earn. And that'll go towards your 4th quarter grade. It's extra credit. So I'm not going to make an offer to students and not to others. So it's the same deal for everybody, whether you're exempt from the final or not. I think we'll say you can earn up to the equivalent of 10 board points, and we'll just take your percentage. And so if you complete 10% of it, you get a board point. Fair? All right. So that's what that's there for. So if you don't do anything, okay, you get nothing. If you do all of it, you get 10 board points, which will probably equate to, I would guess, 3 to 4% on your 4th quarter grade. I don't know. It depends a little bit on who you are. So how many homeworks I've collected and how many days you were absent from warm-ups. So one person's total number of points for a quarter is going to be different from somebody else's. All right. Any questions? I do want to point out one thing. Narose, you brought this up. Which one was it? 15 and 43? Yeah, all right. So 15 versus 43. So for 15, your function was x to the 2/3, was it minus 1? All right. And it was on the interval from -8 to 8. And versus 43, where what the function is just f of x equals x to the 2/3. And here the interval is 0 to 1. So both of these functions are continuous on the whole closed interval, but they're both not differentiable at x equals 0. Because if you take the derivative, say f prime of x is going to be 2/3 x to the negative 1/3, or 2 over 3 cube roots of x. And then you can see, hey, if I plug 0 in, the derivative is undefined. And the same thing happens over here, right? So you have the same exact derivative. So it's 2 over 3 cube roots of x. And so again, f prime of 0 is undefined. So why are you allowed to apply Rolle's and mean value theorem to 15? So why can't you in 15, but you can do mean value theorem of 43? So that gets into the really kind of nitpicky definition of these theorems. So I've been kind of fast and loose with the definitions, but it turns out, and it matters here, that you have to be continuous on the closed interval, but you only have to be differentiable on the open interval, where we don't really care about the endpoints. So continuous here, but differentiable here. Now, in this case, 0 is inside the interval, and so if you're not differentiable somewhere inside the interval, you've broken the theorems, you can't apply them. So that's why 15, you cannot use mean value or Rolle's theorem. But for 43, because the 0 is on an endpoint, we don't really care that you're not differentiable there. So we have to be continuous on the closed interval, which we are, but then we only have to be differentiable on the open interval, where anything goes on the endpoints with the derivative. And so that's why we're still allowed to go ahead and use mean value theorem there. So if you were looking at that as like, hey, what gives? That's why. So that's on me for not being more careful with our definitions. Yes. Yes. The camera is on. Yeah, but that's for my block too. So I have all my Google Meets open on my laptop, so that I don't have to, like, in between class, get into a new Google Meet on all my computers. And it's great as long as these laptops that connect to the cameras don't kick me out because they lose internet connection. I hate technology. 4 and 6, and where's the other one? 1 and 4. Deb and Tanika's rows. Hi. Homework?
No.
What?
No.
No? Aw. That's fair. Which day were you absent? Which day? Friday? Monday. Okay. Were you here yesterday?
Yeah.
Okay.
I'm gonna go to the
Oh, okay. Thanks. All right. Today and tomorrow we're going to wrap things up with chapter 3 stuff. And we're going to look at how to find relative maximums and minimums. So last week we talked about how you find absolute maximums and minimums. And we saw this idea of a critical number. So we saw the critical number is a number that makes your derivative equal to 0 or undefined. And your absolute max and min must happen at a critical number or at the endpoint of a closed interval. Relative maxes and mins can only happen at critical numbers, and that's it. So relative maxes and mins cannot happen at the endpoints of an interval. They only happen within some interval. And a relative max or min could be an absolute as well, but not necessarily. So a relative max or min is just the highest point or the lowest point in its general vicinity. So to do that, to determine where we have relative maxes and mins, we use something called the first derivative test. And really what we're doing is we're checking it using the first derivative to see where is a function going up, where is it going down. And then where you switch from going up to going down is where you have a maximum. And where you switch from going down to going up is where you have a minimum. So talking about the first derivative, because derivatives are slopes, if your slope is positive, that means your curve is going up. And if your slope is negative, it means your curve is going down. So same thing with derivative. If your derivative is positive, the curve is going up. It's increasing. So on this picture down here, this first section, the curve is going up as you move to the right. So this is where the derivative is positive. The middle section, the derivative is negative because this middle section, the curve is going down. So in here, f prime negative. And then over here on the right, the curve is going up again, so f prime is back to being positive. So derivative positive or negative tells us whether the curve is increasing or decreasing, whether it's going up or going down. So for this example, with this graph, we could say, well, f prime is positive on the interval. So start way out here on the left. When does it start being an increasing curve? For when x is way out at what value? Negative infinity. And then it continues to increase until you get to what value? A. And then when does f start to increase again? That's C. And then you continue to increase until where? Yeah, forever. So out to positive infinity. So that would be interval notation for where we're increasing. So f prime is positive, and therefore f is increasing on these intervals. F prime is negative, so it's going down on two intervals as well, actually. So f prime is decreasing from A until where? A until C, yeah, sort of. What's happening right at B? It's 0. So right at B, the derivative is 0. So technically, right at this one moment in time, our derivative is suddenly not negative. So you could kind of break that up and say we're negative from A to B, and then again from B to C. But right at B, the derivative is 0 because we flatten out. Where else does the curve flatten out? At A. So that's another place where the derivative is 0. So derivative is 0 anytime the curve flattens out. And where's the derivative undefined? That's C, because of the sharp turn. So that's kind of just using a graph of a function f to kind of analyze the derivative. When is the derivative positive or negative? Well, that's when the curve f is increasing or decreasing. When is the derivative 0? Well, that's when the curve is flat. And when is the derivative undefined? Well, that's when you see a sharp turn or a discontinuity. So any comments, questions on just picture understanding of the relationship between first derivative and curve being increasing or decreasing? Yes.
Are we supposed to use brackets?
No. Because this is for when the derivative is positive, and right at A, the derivative is 0, not positive. So that's why. But yeah, as in, if you use brackets, would anybody be coming for your head? No, it's not like the worst thing ever. But that's why I'm not using brackets there. And then that kind of gets us into the first derivative test. Now, your first derivative test is on that thing of notes I gave you guys in chapter 3.3. And I believe it's on the Delta Net for this week. So in the notes I gave you, down at the bottom of your chapter 3.3 stuff, there's the first derivative test. Here is, I don't know, another way of saying the first derivative test. So you can look at what's here, or you can look at what's in the notes, and you can decide for yourself what is more understandable to you. So a relative minimum is going to happen where, first of all, you have a critical number. So the derivative is 0 or undefined. And also, the derivative switches sign from negative to positive. Because if the derivative switches from negative to positive, that means your function switches from going down to going up. And at the bottom of that, you have your critical number and your minimum. So over here on the bigger picture, we can see a place where the derivative is 0, but there's not a minimum because we don't switch from going down to going up. We flatten out, and then we keep going in the same direction. So this point right here at B, it's a critical number because it makes the derivative 0, but it's not the place where you have a relative max or min because the derivative doesn't actually change sign. It's negative, it's 0, and then it's still negative. So we need both of these things to happen. We need the derivative to be 0 or undefined, and we need the derivative to switch sign as you go from one side to the other side. A relative max works the same way, except we switch the other direction from derivative being positive to negative. So we're going up, and then we're going down. So here's an example of what that can look like. You've got one where the derivative is 0 and one where the derivative is undefined. So that's your first derivative test in a nutshell. If you have a critical number, so the derivative is 0 undefined, and you don't switch signs from negative to positive or vice versa, then you don't really have a max or min. You have one of these things. So that's your first derivative test, expressed another way than what's in the book or what's in the notes. So what we're going to do now is kind of work through several examples. First of all, just how do you find intervals like this from an equation? And then also, how do you then extend that and find the relative maxes and mins on some interval? So I'll leave that up, and hopefully I'll remember not to erase it after class so I don't have to write it again for plot 3. You guys can write that down while I get up a couple examples here. All right, before we do any examples, any questions with anything there from the notes and kind of big picture stuff there? Okay. Ready for examples? Okay. So, one of the things you'll have on the final exam on the free response, and also something that'll probably show up on 1 or 2 multiple choice questions, is something along these lines of, here's a function, where's the curve increasing? Or here's a function, where's the curve decreasing? And the way you do that is you start by finding the derivative and then use the derivative to get the critical numbers. So maybe I'll write down here a sequence of steps. Step 1, find f prime of x. Now, maybe I'll be kind enough and give you f prime of x, the example 1b. But often, you'll have to find that for yourself. Once you have f prime of x, find the critical numbers. And remember, that's f prime of x is 0 or undefined. So let's take our function and differentiate it. So what is f prime of x here? So that's going to be 3x squared minus 3x. And then you think to yourself, self, is that ever going to be undefined? No, because there's nothing weird here. There's no fraction, no negative exponent, nothing to cause division by 0 anywhere, so that will never be undefined. So it will only ever be able to equal 0 to give us critical numbers. So you set it equal to 0, and what can you do to solve this? Take the 3x out, what's left behind? And so x equals 0 or 1. So you've got your critical numbers. What you're going to do is use those to break up the domain. The domain is probably all real numbers, or it's specified by some given interval. So here, this is a polynomial. The domain is all real numbers. So what we do is we take the domain and break it up into 3 sections using these critical numbers. So step 3 is break up domain into smaller intervals using your critical numbers. And you're going to basically create like a table of intervals, and you're going to check each interval to see is the derivative positive or negative in this interval. So domain, you go from minus infinity to 0, and then you go from 0 to 1, and then you go from 1 to infinity. So those are your 3 intervals. So call this table of intervals. Make sure you work from left to right with these things. All right? You don't want to go from minus infinity to 1, and then from 1 to 0, and then 0 to infinity. That'll just be weird and confusing because you'll have like overlapping backwardsness. So make sure you're working from the left to the right all the way through. Once you've got your table of intervals, plug a value from within an interval to the derivative and see if you get a positive or a negative. You don't even really care what the value is, you just care positive or negative. So you pick a number from inside this interval from minus infinity to 0. What's a good number to choose in there? Not 0, negative 1. So you don't want to choose one of the endpoints. You already know the derivative at these endpoints. They make the derivative 0. That's what makes them critical numbers. That's why we're using these. So you don't want to use 0 or 1. You want to use a number inside the interval. So negative 1 or negative 2 or negative 800, something like that. So you plug negative 1 in here. And what's 3 times negative 1 squared minus 3 times negative 1? 6. All right, so that equals 6, which is usually positive. Right, because negative 1 squared is 1, 3 times 1 is 3, negative 3 times negative 1 is positive 3, 3 plus 3 is 6. Yeah, so you get 6, that's positive, and therefore, f is doing what on this interval? Increasing. So we pick a number from within this interval, and then that represents the entire interval. And whatever f prime is at negative 1, f prime is going to be the same sign all the way through that interval. So if f prime is positive all the way through this interval, we know that f is increasing on the interval minus infinity to 0. Then you do it again for the next interval. So in this next interval, you pick another number, this time between 0 and 1. Probably 1/2 is the best option. And here you might want to rely on a calculator a little bit. Plug in a half to your derivative and see, am I positive or negative? I'd be shocked if it was 0. It's not. I think you forgot to square the 1/2. Yeah, 1/2 squared is 1/4. That's true. So 3/4 minus 3/2. unless you're going to claim that 3/4 and 3/2 are the same thing. So what's 3/4 minus 3/2? It's negative, right? So it's negative. And it's negative 3/4, but more importantly, it's negative something. So because it's negative, then we conclude that f is decreasing on that interval from 0 to 1. And then you do it again for the last interval. So the more critical numbers you have, the more obnoxious this is, because then you have more intervals to check. So you hope and pray only one critical number, please, so that you only have 2 intervals. So over here, pick a number between 1 and infinity. 2 sounds good. You plug it into the derivative, and you see what you get, positive or negative. So when you plug in 2 to our derivative, what do we get? Positive 6, so positive. And since it's positive, that tells us f is increasing. And that's on the interval from 1 to infinity. Ta-da! Laura. Oh, yes. So we're using the critical numbers to split the domain into intervals. The more critical numbers you have, the more splits you have to make. So if we also had a critical number at 5, then we'd have not from 1 to infinity, but from 1 to 5, and then from 5 to infinity. So the more of these you have, the more of these you're going to have, and the more stuff you have to plug into the derivative to check. So I guess to finish our steps, once you broke the domain up into smaller intervals, what we did was we checked a value from within each interval into f prime of x to see if f prime is positive or negative on that interval. And if f prime is positive, f is increasing. If f prime is negative, f is decreasing. So that kind of summarizes what you do. And to do the first derivative test, to find a max or min, you do exactly the same thing, and you take one more half step and draw a conclusion. And you can say, well, if f was if f was increasing and then decreasing, then right at x equals 0, where we switch, what does there have to be? A maximum or a minimum or neither? A max, because we're going up, we reach x equals 0, and then we're going down. So that means there has to be a max at x equals 0. And to find out what it is, plug that into the function. We'll come back to that in example 2. And here, we're decreasing, hit 1, and then increasing, so we have to have a minimum at x equals 1. And then again, to find what the minimum is, plug that into the function, you get your minimum. Grace?
Will there ever be one where like it's 0?
Inside the interval?
Yeah.
No, because these points on the edges are all the places that, so you just make sure you don't plug in one of these values to the derivative. If you do get 0, that means either you missed one of your critical numbers, which is always possible, or you plugged it into the derivative wrong and you're like subtracting or adding stuff incorrect. But as long as you get all your critical numbers, whatever you plug into the derivative from within an interval will never give you 0. What could happen is that you could have consecutive intervals that are doing the same thing. So you might have an interval that's decreasing and then another interval that's decreasing, and then you just don't have a max or a min at that changeover point between the intervals. Any other comments, questions to follow up example 1? So let's look at example 1b, which is similar but not totally the same in terms of what you're doing. And then we'll look at example 2, where we actually go ahead and find the relative extreme. So, how is the given scenario different from what we just did in example 1? So, what about it? We have the derivative. In the first one, we were given f of x, and we had to find the derivative. Here, do we know what f of x is? No, we know what f prime of x is. So here we are given the derivative. Hooray! We don't know the original function f of x, but we can still find out where the unknown function f of x is increasing or decreasing by analyzing his derivative. So we don't get to see f of x. We don't know what it is. We don't know what it looks like. We don't know its equation. But we can at least find out where is it increasing and decreasing based on its derivative, which we do. All right? So in part A, we just find the critical numbers. So we just take the derivative that we already have and do what with it? Yeah, equal it to 0. So part A, take the derivative and set it equal to 0. That'll never be undefined again, so we don't need to worry about that. And lucky for us, we have the derivative already. So we have 3 times the quantity x minus 1 times x minus 2 times x minus 3, thank you, squared equals 0. So what are our solutions for x? 1, 2, 3, and not 0. Because this is not 3x. It gives us 3. So you could take the 3 factor out front and say 3 also equals 0, and then you would say, no, it doesn't. But since there's no x on that 3, that doesn't give you another solution. So yeah, let's out that for that little detail. Once you got your critical numbers, do the same thing as before with a table of intervals. So what's our first interval going to be from? Negative infinity until 1, and then 2 to 3, and then 3 to infinity. So you can see more critical numbers. We got 3 here as opposed to only 2. More intervals. Once you got your intervals, check a value from within each interval. And what's a good number to check between minus infinity and 1? 0 makes sense. So if you plug in 0, 3 times negative 1 times negative 2 times negative 3 squared is what? I don't know. Well, is it positive or negative? So I have 243. I have 24. In my head, I have 54. I have 54. 54? Okay. Well, what's negative 3 squared? 9 times negative 2. Negative 18 times negative 1. 18 times 3. 54. All right, cool. And so since that's positive, we say f is increasing. Then things get annoying. What should we choose between 1 and 2? 1.5. So plug in 1.5. Use your calculator for that, please. Well, maybe we can get away without a calculator. If we don't care about the value, we only care about positive or negative. So what's 1.5 minus 3? Positive or negative? Negative. But a negative squared is positive. All right, so we have a positive times, what's 1.5 minus 2? So a positive times a negative is negative. 1.5 minus 1 is, so a positive times a negative is negative, and a 3 times a negative is negative. So it's negative. And really, the actual value is super irrelevant. We only care is it positive or negative. So if you have a decimal that you have to check, and you don't feel like getting out your calculator, you can kind of do that logic process and say, well, that part's going to be negative, and a negative times a positive is a positive, and whatever. So this is decreasing that. Because that's really all we care about finding. So f is decreasing from 1 to 2. 2 to 3, what do we want to check? 5. So check 2.5 minus 3 is, squared is positive. So we have a positive times 2.5 minus 2 is positive times a positive is positive. 2.5 minus 1 is positive times a positive is times a positive 3 is positive. So everybody's positive here. So you got a positive, and therefore F is doing what? Increasing. And then finally over here, 3 to infinity, what do you want to check? 4 sounds good. 4 minus 3 is 1 times 2 times 3 times 3. Positive or negative? Positive. So F is increasing some more. So we could say, hey, where are we increasing and decreasing? Maybe so we can see things a little more clearly because everything's crammed together. We're increasing from minus infinity to 1, and then again from 2 to 3, and then again from 3 to infinity. And we're decreasing from 1 to 2. At what x value will there be a maximum? At 1. So as at 1, we go from increasing to decreasing. So max at x equals 1. Now here, because you don't know the f of x function, we can't find out what the actual max is. All we can do is say, I don't know what it is, but it happens at 1. And where would we have a minimum? 2. So we'll have a minimum at 2. And then that's it, right? Because at 3, we're increasing flat at 3 and then increasing some more. So there is no maximum or minimum at x equals 3. It's just kind of one of those weird places where we're going up, pause, and then keep going up some more. So that's another kind of first derivative test sort of problem where you find out where are we increasing, where are we decreasing, where will there be a maximum or minimum. The main difference between this one and the previous one is here we were given the derivative. There will be a problem similar to this on the final exam, as opposed to the first one where it was giving you the original function f of x to begin with. So I think on the final, this sort of thing is on the open-ended, and that sort of thing is more likely to be on the multiple choice. Sort of. So you can find f of x if you do an integral. So you would have to, this is an integral symbol. So you'd say f of x equals the integral of 3 times x minus 1 times x minus 2 times x minus 3 squared dx. What the hell is a dx? Don't worry about it. Now, in order to get this integral, I'd want to multiply this all out because integrating it the way it is going to be awful. Just like if you tried to take the derivative of this, that would be nasty, like multiple product here. But yes, you could get f of x sort of, but only sort of because once you get the integral, you won't know what the constant term is. So you would get some function, and then everything involved is going to have an x, and then you don't know what the constant is. So you would just tack on a plus c, and c is just, I don't know, it's a constant. And unless I have an actual point on the curve, I can't find out what plus c is. So then you just let it be plus c. That's not on the final. That's chapter 4 stuff. So don't worry about it. But that's like a good thing to point out. And somebody else had a comment earlier that was helpful. For the board point. Oh, it was your thing about 13. All right. Any follow-up comments or other questions with example 1b? All right. I think last one for today. And then we'll return to do more of this tomorrow. But this, I think, kind of gives us really everything that I was hoping that we would get through this week at this point. All right, so let's actually go ahead and get the maximums and minimums. So we're looking for the relative extreme and not the absolute. So I don't really care what happens at the endpoints. If I want an absolute extrema, I would also need to check the endpoints, but I don't care here. I only care about relative extrema, and they only happen inside the interval. And what I'm going to do is exactly the same as what we did over there. Get the derivative, find the critical numbers, make a table of intervals, check each interval to see where are we increasing, where are we decreasing, and then go that one extra step where we then kind of draw the conclusion about where we have maxes and mins and plug them into the function f of x. So, step 1, get your derivative. What's f prime of x? One half minus cosine x. Then, step 2, you find your critical numbers. What do I do with the derivative? Make them equal to 0. So we have a half minus cosine x equals 0. Oh, fun! Trig. Cosine x equals what? 1/2. Unit circle time.
Wouldn't it be negative cosine?
Yeah, but then this would be negative 1/2.
Right.
So those will cancel out. What angle makes cosine be a half? I know. That's why I asked it. So this is pi over 6. This is pi over 4. This is pi over 3. This is 1 comma 0. If this is a 1 comma 0, then what's this number here? Root 3 over 2. And cosine tells us to look at the x coordinate, so I'm not going to bother with y. Then this is root 2 over 2. So then this is 1/2. Oh, ding, 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 ding. So we have the x coordinate 1/2 attached to the angle pi over 3 on the unit circle. So cosine equals a half for the angle pi over 3. But wait, there's more, because what kind of 1/2 is this? Positive, and what other quadrant besides 1 is cosine positive in? Oh, fun, quadrant 4. So what's the quadrant 4 version of pi over 3? I love you guys. If you are not one of those people who said 5 pi over 3, I love you too. But here's how you get to quadrant 4. Go all the way around, that's 2 pi, and then back up by pi over 3. So that puts you at 5 pi over 3. So now you have all 2 of your critical numbers. Now I heard somebody say wait, so now I'm willing to do that. Is there a reason somebody said wait? I'm waiting. All right, so now that you've got your critical numbers, we can say goodbye to the unit circle, see you, and do your table of intervals. Now here, our table of intervals should start at 1. That's 0. So we're not going to go all the way out to minus infinity. We're only going to go all the way out to 0. So we'll start at 0 and then go until pi over 3. And then we'll have from pi over 3 to 5 pi over 3. And then we'll have from 5 pi over 3 all the way to 2 pi. And you're going to take a value from within each of these things and plug them into the derivative. Now, are you allowed to use your calculator for this? Yeah, absolutely. Because all we care about is the derivative positive or negative. So, what's a good value between 0 and pi over 3? Pi over 6 is good. All right, pi over 6. What's cosine of pi over 6? Is 1/2 minus root 3/2 going to be more or less than 0? Well, who's bigger, 1/2 or root 3 over 2? So 1/2 minus root 3 over 2. Who's bigger, 1 or root 3? Root 3. So 1/2 minus root 3 over 2 is negative. And that's all. But we don't care what it is. We care that it's negative. And if you're like not sure, calculate it. Do that. So that means f is decreasing on that first section. Then from pi over 3 to 5 pi over 3, what's the best or least bad option? Probably pi. And then over here is kind of the worst scenario. What's 5 pi over 3 as a decimal? Actually, you know what? We can do over 6 again. What's the quadrant 4 version of pi over 6? Yeah, so I would do that. And then once you've got that, who's positive, who's negative, and so on, draw your conclusions, plug into the function to see max and min. We'll return to this tomorrow.